All right, today we're going to look at the squeeze theorem and see how that applies to limits and how you can use the squeeze theorem to determine the value of a limit, even when you can't actually break down that limit analytically. And you'll see why we're calling it the squeeze theorem in just a second. So we're going to start off with our definition, or our theorem rather. The squeeze theorem is often called the sandwich theorem as well, because what we're essentially going to do is sandwich the function we want to take the limit of between two functions that will approach the same value at our c. And so that will allow us to predict what our c value is without actually analyzing the limit at that point. We're analyzing the limit of two functions that are kind of like upper and lower bounds for our function. So what this limit, or what this theorem says, is that if some function h of x is less than or equal to our function f of x, which is less than or equal to some other function g of x. So we have our f of x functions, the function we care about. We have some lower bound for all values of x. H of x is going to be less than f of x. And then for all values of x, g of x is going to be greater than. So we're sandwiching our f of x between this h of x function down below and our g of x function up above. So if we have this situation, and if the limit as x approaches c of h of x equals L, and the limit as x approaches c of g of x equals L. So notice at some unknown c value, these two limits converge to be the exact same value, and they may kind of head off and go to different ways otherwise, but if at a c value, they're the exact same value. And if f of x is continually sandwiched in between them, then it has to imply that the limit as x approaches that c value of f of x will also equal L. So we're going to look at Desmos first to see an example of this, and then I'll show you how it breaks down analytically. So our first example that we're going to look at is the limit as x approaches 0 of x squared multiplied by the cosine of 1 over x squared. And clearly this isn't something, so if we wanted to break this down analytically, first of all, we would go and we would try to substitute in 0 for x squared. But we can't do that, right? Because 0 is in the denominator. And so that leaves me finding the cosine of some undefined number, which we just can't do. And then if I were to try to analyze this by thinking about numbers that are really, really close, it all kind of close to 0, but not actually 0, I'm finding cosine of some really large number going to infinity, but cosine oscillates, right? It goes from -1 to 1, -1 to 1, -1 to 1, -1 to 1, -1 to 1. And then I'm multiplying by x squared, which is 0. So I'm multiplying 0 by some number that's never like quite pinpointing, right? It's just going back and forth between -1 and 1 and passing through, a whole slew of numbers in between. So what we're going to do is let's just go ahead and take a look at what this looks like graphically first. So looking at this, we're going to have, I'm first going to show you what this graph looks like. So it looks kind of crazy, right? It extends indefinitely to positive infinity and negative infinity as our numbers get large enough, because notice that if I'm going to positive and negative infinity, this actually makes sense. This is getting really, really positive and really, really, really large. So I'm doing 1 divided by a really, really large number. Which means it's getting closer and closer and closer to 0. So I'm finding cosine of 0, and cosine of 0 is 1. So if I'm multiplying this insanely large number by 1, it's going to some positive infinity. So that's why this function is going off in either direction. But we don't care about it going to infinity in this problem. We care what's happening at 0. And notice as my function gets closer and closer to 0, it looks more and it's like oscillating like crazy, right? So to the point where it almost looks like it's completely filled in. So let's bound this function by a function that we know lies below and a function that we know lies above. And I'll show you how I got these functions in just a second. But I'm going to go ahead and bound this by a positive x squared. Hold on, let me zoom out a little bit so you can see. So that's positive x squared. And then I'm going to bound it by on the lower bound by a negative x squared. And notice how this function just fits so nicely between. It's not always going to be this case where it's just like perfectly fits the function. But notice that that blue function, my g of x, is always the upper bound, and my h of x is always that lower bound, and it's just nicely sandwiched in between there. So because of that, we can analyze the limit as x goes to 0 at g of x, and the limit as x goes to 0 of negative x squared, which is h of x. And if I sub 0, so if I analyze the limit and sub 0 into each of these expressions, I get 0. Since both those limits equal each other, we can assume that the limit of f of x as x goes to 0 is also going to be 0. So let's jump back and see what that looks like analytically. So graphically, that's what's going on. You saw that check. It definitely is going to 0. X squared is, negative x squared is. So I have that parabola up top, parabola below, and that means that f of x function, which isn't a function we really know the shape of until we graph it, must also be approaching 0. So the way that we're going to develop this without having to use Desmos or without using a graphing calculator is just to break down what we do know. So I'm going to look at this function. This isn't my cause of concern. I know what x squared looks like. It's really this cosine that is causing some issues. So I'm going to start off by writing cosine of 1 over x squared. And what's nice about our sandwich theorem and trig functions is that cosine and sine are actually already sandwiched between two values, right? So cosine lives between -1 and 1. It oscillates between those two values. No matter what x value I put in, I'm either going to get a value greater than -1 or less than +1. But I need x squared times this. So I'm going to go ahead and multiply this side by x squared. I'm going to multiply this middle region by x squared, because remember with the compound inequalities, what you do to one part of that compound inequality, you have to do to every single part. So I now have a negative x squared less than or equal to x squared multiplied by cosine 1 over x squared less than or equal to a positive x squared. All right. Now that I've kind of formulated and I have that f of x function in here, I want to take my limit. So I'm going to take the limit as x goes to 0 of a negative x squared. The limit as x goes to 0 of x squared multiplied by the cosine of 1 over x squared. And the limit as x goes to 0 of x squared. And notice I'm not doing all of this work for fun. This is how it needs to be written so that it's done mathematically accurate, or it's done accurately in a mathematical way. So I'm going to sub in 0 now. The limit as x goes to 0 of this function, negative x squared, is just 0. I can't analyze this yet. I don't know. We already talked about that. I can't sub in for that denominator because I get an undefined expression within my cosine, and that's not feasible. And then the limit as x approaches 0 of x squared is also 0. So notice now this function is living between 0 and 0. So there's no other value that it could possibly be, right? If it's somewhere between 0 and 0, then 0. So we can say by the squeeze theorem, the limit as x goes to 0 of x squared times cosine of 1 over x squared must equal 0. And we're good. All right. So this is how, if we're asked to find something like this, this is the process that we would need to kind of work through to be able to verify that that limit is in fact 0. We would need to show all of these steps to be able to cite the squeeze theorem. Let's go ahead now and take a look at a situation where we know that the squeeze theorem is going to work, or maybe it's not going to work, and see how we can kind of build from there. So this next example is going to state, let's let g and h be functions defined by g of x equal to cosine of pi over 2x plus 2, and h of x equal to x squared plus 3. Okay, here's a big word in math, if. So we're going to have to verify whether or not we can even use the squeeze theorem or not. If a function, if f is a function, cross that out. So if f is a function that satisfies g of x less than or equal to f of x less than or equal to h of x for -1 to 5 inclusive, what is the limit as x goes to 0 of f of x? So the first part is asking, it's giving us the information, right? And then it's having this if. So that means we need to verify if this condition is even true. And then from there, if it is true, we can find the limit as x goes to 0. So first, let's verify that this is even true, that f of x, that there is some function that lives between these, right? And more specifically, even if it just lives between, in order to use the squeeze theorem, we need to take that one step further. And this limit as x goes to 0 of g of x needs to equal the limit as x goes to 0 of f of x, of h of x, I apologize. So let's go ahead and set this up. I'm going to take the limit as x goes to 0 of cosine of pi over 2x plus 2. So I'm going to put 0 into this function. So I have cosine of 0. Cosine of 0 is 1 plus 2 gives me 3. And remember, go back and really make sure you know that unit circle, because you're gonna have to analyze trig functions from time to time, and you want to really have that down. And then the limit as x goes to 0 of x squared plus 3 is 0 plus 3, which also equals 3. So right now we know that g of x is falling between these two values. We're in good shape. So now we can assume, so by the squeeze theorem, the limit as x goes to 0 of f of x must equal 3, because it equals 3 at both of those spots. And let me go ahead and show you that one on Desmos as well, because I think it's just nice to actually see the visual here. Yep. So let me turn off these guys. All right, so this was our g of x function. This is my h of x function. So notice this one, there's some f function, we don't know what it is this time, but notice that they have that same value. And so whatever that x function is, it's telling us that it's bounded by these two. So something's going on here. And what we just needed to verify was that those limits equaled the same value, so that we could predict at 0 what the limit of f of x must be. All right, let's go back and do one more example like this. So, there we go. In this instance, I'm not going to put all the verbiage. We're going to let g of x equal negative x squared plus 2x subtract 3. We're going to let h of x equal 2x plus 1. We're told that the function does satisfy the fact that g of x is less than or equal to f of x is less than or equal to h of x. So we know that to be true, but we want to know if we can use the squeeze theorem. So does the squeeze theorem apply? And if it does apply, what is the limit as x goes to 2 of f of x? So we're told the first part of the condition that is true. So f of x lives between these two functions. But in order to determine this limit, not only does it need to live between these two functions, but it also, this limit as x goes to 2 of g of x must also equal the limit as x goes to 2 of h of x. So I'm going to go ahead and analyze those two limits and see if they're equivalent. So we have a negative x squared plus 2x subtract 3. I substitute in, I get a negative 4 plus 4 minus 3. So I get a negative 3 for g of x. And the limit as x approaches 2 of h of x is going to be 5. So since these two limits do not equal each other, we say that we cannot determine the limit as x goes to 2 of f of x. So because these two don't equal each other, we cannot determine the limit as x goes to 2. All right, for our last type of problem, and you're going to go ahead and practice all of these types immediately after, we are going to let f of x be equal to 1 subtract cosine of x all over 2x. We're going to let g of x equal x cubed times the sine of 1 over x. And we're going to let h of x equal x over sine of x. And for all of these, we're stating that x cannot equal 0. And we're stating that all of these are true. So all the inequalities that I'm going to write down below are all going to be true for when x does not equal 0. So obviously x can't equal 0 here, here, or here. And so in each situation, x cannot equal 0. And we want to know whether or not the squeeze theorem can be applied for each of the inequalities that I'm setting up. And we're looking as x approaches 0. So what we're trying to determine is the limit as x goes to 0 of f of x. And clearly we can't analyze it here, right? Because we have this x in the denominator. So we run into a little bit of an issue. So let's take a look and see if this first inequality would be a good inequality to set up. We have negative 1/2 less than or equal to our f of x function less than or equal to x squared plus 1/2. So in order for this to be a good situation for us, we want to take the limit as x goes to 0 of all parts. And it should be that the left side equals the right side. So notice when I substitute in 0 here, there's no x value. So I'm just going to get a negative 1/2 out. And when I substitute in 0 here, I get a positive 1/2. Notice that negative 1/2 and positive 1/2 don't equal each other. There's an infinite number of values between negative 1/2 and positive 1/2 that f of x could be. I'm sorry, I should put the limit here as well. So the limit as x goes to 0 is somewhere between negative 1/2 and 1/2. So we could not determine. This inequality would not allow us to determine whether or not, or what value f of x is going to hold. So no, this is not a good, this would not be an inequality that would work. Let's look at the next one. Let's say we go from negative x cubed. Now we're analyzing g of x, so that's this one right here. And again, for this one, we're doing the limit as x goes to 0. So I'm going to go ahead and set that up. The limit as x goes to 0 of a negative x cubed. The limit as x goes to 0 of g of x. And the limit as x goes to 0 of x cubed. So now when I analyze these limits, I put 0 in here. Awesome. I get 0. Cool. The reason I shouted out awesome is because I could see ahead that this is also going to be 0. So yeah, this one works. And we can conclude that the limit as x approaches 0 of g of x is going to be 0. Yay. All right. I'm just going to erase this guy so I have enough space for this last one. I want to clear everything because then I'll lose the whole problem. Okay. All right, our last problem is 1 subtract x squared is less than or equal to h of x. So now we're doing this x over sine of x, which we actually already know the answer to, right? But we'll analyze regardless. So I'm going to take the limit as x goes to 0 of 1 subtract x squared, the limit as x goes to 0 of h of x, and the limit as x goes to 0 of x squared plus 1. Now if I sub in 0 here, I get 1. If I sub in 0 here, I get 1. So we now know that the limit as x goes to 0 of x over sine of x equals 1. And that was also true because this is one of those ones that we're memorizing, right? So the limit as x goes to 0 of sine of x over x is the one that we have memorized. But the reciprocal is also going to be true because the reciprocal of 1 is also 1. So we're just looking at a ratio with those types of problems. So this one works as well. Yay. All right. So from here, you're just going to have some practice problems. You're going to have a page. I want you to work through it on your own, or you're going to have a problem rather. I want you to work through it on your own first, and then watch my video to see how you do. All right, all of these problems are going to be similar to the ones that you saw in the first example that I did within your notes. So we're trying to actually find the limit of something that, again, notice the denominator here. I can't sub in 0 for any of these ones because if I were to substitute in 0, I would end up just kind of bouncing between -1 and 1. And if you were to graph these in Desmos, you would see the same thing. You really would have to zoom in to see what's occurring at 0. So let's start with this first one. I'm going to kind of focus in on this cosine of 1 over x because I know that that's the part that's really kind of messing with me. So I'm going to say, all right, well, I know for a fact that cosine of 1 over x oscillates between -1 and 1. Now I need to have this, I need to build this function. So I'm going to multiply everything by x. So now I have the negative x, I have x cosine of 1 over x. So I now have my f of x function in there, and then I have x. So now we're saying that this function lives between the function negative x and the function positive x. And it's going to live right in between there. And then what we're going to do is we're going to take the limit as x approaches 0, the limit as x approaches 0, and the limit as x approaches 0. I should have written that as its own line. But when I analyze that, I get 0 is less than or equal to x cosine 1 over x, which is less than or equal to 0. So we can conclude that the limit as x goes to 0 of x multiplied by cosine 1 over x equals 0. All right, for the next one, again, I'm going to start right in here, and you're going to end up with a similar solution, but it's all about the process. We're going to bounce between -1 and 1. Then we're going to take the limit as x goes to 0. Oh, I'm sorry, skipping steps. Now I need to include this x squared. So I'm going to multiply each of these expressions by x squared. So I have a negative x squared less than or equal to x squared sine of 1 over x squared less than or equal to x squared. Now I'm going to take the limit as x goes to 0 of each of these functions. And again, we get 0, 0. So we know the limit as x goes to 0 of x squared sine of 1 over x squared is going to equal 0. You should just follow the exact same process for question number 3. So it's bouncing between -1 and 1, multiply each side by x this time, take the limit, and again, you'll get that this limit equals 0. That's not always going to be the case. It just happens to be the case for each of these problems. You won't always get 0 out. All right, 4 and 5, these next two questions are similar to the next two questions that we did in our notes. So we're letting g of x equal x squared subtract 3 of x, and h of x is 2 subtract 2 of x. We're told that it does satisfy that g of x is the lower bound and h of x is the upper bound. We want to know what the limit as x approaches 2 is for this one. So in order to do that, I need to just verify that both of these limits of g of x and h of x are also approaching the same value at 2. So if I sub in here, I get 4 subtract 6, which is a negative 2. And then if I sub into h of x, using our limit notation, again, I get negative 2. So as a result, by the squeeze theorem, I can state that the limit as x approaches 2 of whatever that function is, must be negative 2. Let's check this next one. We have the limit as x approaches negative 1 of cosine of pi times x plus 2, subtract 3. And we're going to do the limit as x approaches negative 1 of x squared over 2 plus x subtract 7 halves. So when I substitute 1 in here, I'm going to actually write this one out. I have cosine of, if I put negative 1 in, it's going to be negative 1 plus 2, which is 1. So cosine of pi, subtract 3. Cosine of pi is a negative 1. So we end up with a negative 4 as our solution. Over here, when I substitute in a negative 1, I get a positive 1/2. Subtract 1, subtract 7 halves. So I'm going to combine these fractions first. That gives me a negative 6 halves. Subtract 1, which is a negative 3, subtract 1, so I get a negative 4. So I'm good to go. So by the squeeze theorem, we know the limit as x approaches negative 1 of some function f of x must equal negative 4. All right, for this last section, it's similar to the last problems that we have. So now we're given some inequalities for our functions f and g, and we need to know if the inequalities that we've set up are going to work. So this first one's kind of straightforward, right? We have a 1/5 and a 1/2. So it's as if the limits were already analyzed for us. But 1/5 does not equal 1/2, right? So the squeeze theorem cannot be applied. And as a result, we cannot determine the limit as x approaches 0 for f of x. There's not really much we need to show for that one. This next one, we do actually need to analyze our limits. So we're going to take the limit from the left. And our limit, so the limit of this left-hand side of the inequality, the limit of the right side of the inequality, if I sub in 0 here, I get that this function lives between 1/2 and 1/2. So it's equal to 1/2. So by the squeeze theorem, we know that the limit as x approaches 0 of f of x is going to equal 1/2. So yes, this inequality would absolutely work. For the next one, we again can sub in those limits, analyze as x approaches 0 for some g of x. If I were to substitute 0 in here, I would get that this function is living between 0 and 0. And so this would also be a yes. And the limit as x goes to 0 of g of x would be equal to 0. Our last one, notice that I do limit as x goes to 0 of negative 1 over x. I have the limit as x goes to 0 of g of x. And lastly, I have the limit as x goes to 0 of 1 over x. So I want you to picture for a minute what the function 1 over x looks like. That's that rational function, right? And when we're looking at that rational function, I have an asymptote going through my y-axis. And that asymptote is going to be going towards, so coming from the left, the limit coming from the left is going towards positive infinity. The limit coming from the right is going towards negative infinity. So this limit itself doesn't even exist. And then same over here. As x approaches zero, as it's approaching zero from the right, right? This one is actually now going to negative infinity because these values down here are getting closer and closer to zero. So we have like 1/8, 1/9, 1/10, 1/100th, 1/1,000,000th. And if I do 1 over 1/1,000,000th, that's going to give me a million. So I have a negative 1,000,000. So these are getting really, really close from the right to going to negative infinity. From the left, I'm putting in like negative 1 over 1,000,000, which is doing negative times a negative. That's giving me like a positive 1,000,000. So from the left, it's giving me one value. From the right, it's giving me another value. This limit also does not exist. As a result, I'm sandwiching this limit as x goes to 0 of g of x between two limits that do not exist. So this cannot be determined. This would not be a good way to line this one up. This guy for g of x is great. This would not be a great way. We would not be able to determine based off of this inequality.